In the next few videos, we're going to discuss and to prove those properties of prime numbers which we will need in the development of RSA cryptography. So just recall that the prime numbers are those natural numbers bigger than 1, which are divisible only by themselves and 1. Or equivalently, those positive integers bigger than 1 that cannot be factored into smaller integers. So examples 2, 3, 5, 7, 11. And on the other hand, the following are not prime. 4 because it's 2 by 2, say 8 because it's 2 by 2 by 2, 12 because it's 2 squared by 3. They're not prime. They can be factored into smaller integers. The primes less than 500 are in this list here, and there are 95 of them. And in general, the primes are going to be relatively common. And we'll discuss that later on when we discuss the prime number theorem. So if we're going to factorize, for example, a number like 280, then we can write it, for example, it's not a prime, so we can write it in many ways as a product of two smaller integers. I mean, we could write it as a product of three smaller integers, or 4 in this case. But we can, if it's not prime, we can, which it's not, 280, we can certainly write it always as a product of two smaller integers. Let's choose 4 and 70. So that means 280 is 4 multiplied by 70. Now 4 is itself a product of 2 and 2, and 70, I can write it various ways, but it's a product in particular of 7 and 10. So that 280 is a product of these 4 integers. 280 is 2 by 2 by 7 by 10. But 10 is not prime. It can be factored again into 2 times 5. And so we have, at each level, products which give us 280. At this bottom level, we have 2 by 2 by 7 by 2 by 5 is equal to 280. And if we arrange the smallest factors first, the smallest prime factors first, we have 2 cubed, these 3 2's here, times 5 times 7. Alternatively, we could proceed following the second tree. We can write 280 as 10 times 28. The 10 we can write as 5 times 2. The 28 we can write in a number of different ways, but we can write it, for example, as 4 times 7. And then the 4 is further factored into 2 times 2. And this time we get 5, 2, 2, 2, 7. But notice that it's the same. After we rearrange the smallest primes first, 2 cubed, then times 5, and then times 7. So let's just do one more. Let's write the 280 as 7 times 40, which is just the reverse of what we had over here, but now we're going to factor these slightly differently. Oh no, sorry, it's not the reverse. 280 we'll write it as 7 times 40. 40 I'll factor as 4 times 10, and 7 was prime, so it's just 7. So once again we have that 280 is 7 times 4 times 10, and 4 can be further factored now into primes, 2 by 2, and 10 into 2 primes, 5 times 2. And once again, after rearranging, we get the same as before, 2 cubed times 5 times 7. So, based on that, we have, and we'll prove in a minute, the factorization theorem, that every natural number bigger than 1 is a product of primes. So that's the existence. You can actually factorize every number into primes in exactly one way up to reordering, and that's the uniqueness. So we followed a number of different factorization trees. Each one of them gave us, in the end, the same product of primes after reordering. You can think of primes as the atoms or the basic building blocks for multiplication, and hence their importance in arithmetic. And just one more remark. Why is 1 not considered to be a prime? Well, if 1 were a prime, then we could write 12, as well as writing it as 2 squared times 3, we could write it as 1 times 2 squared times 3, or we could write it as 1 times 1, in other words 1 squared times 2 squared times 3, or 1 cubed times 2 squared by 3 times 3, and so on. So we wouldn't have the same uniqueness of factorization as we do if we exclude 1 as a prime. So that's the reason that we don't include 1 as a prime.